I'm back. Now we're going to go to the next section, which is types of chemical reactions. Okay, we have special names for different types of chemical reactions, and that's what we're going to talk about in this section. Okay, when you burn a candle, you are actually doing a special chemical reaction, and it's called combustion. Okay, so combustion is really, for the most part, is a fancy name for burning. Okay? And what do you need to burn something? Well, you need oxygen. So one of the reactants is always going to be oxygen in a combustion reaction. All right, so we're going to talk about 5 general types of reactions in this section. And why do we do this? It helps you predict the products if you know what type of reaction you're talking about. Okay, and the 5 types of reaction are called combination. Now, I'm going to also call combination something else. We often call this a synthesis. Synthesis reaction, which means putting together. Combination means to combine or put together. Synthesis means the same thing. I like the word synthesis because I think it's a better word to use to describe that. Decomposition is the opposite of that. It means taking it apart. Single replacement, I call this going to the dance and having your date taken away by somebody else. Okay? Double replacement, I call the square dance reaction because you have 2 couples and what happens is that they switch partners. Okay? And finally, combustion, which we just talked about with the candle. It's basically burning something with oxygen. Now, sometimes you have things that actually can fit in more than one of these situations. Okay, but for the most part, you may be able to choose one that better fits, even though it might be more than one of these. All right, so we're going to talk about each one individually. Okay, combination reactions, or as I call them, synthesis reactions. Okay, as you can see, they even agree with me. They just like to use combination. I think synthesis is much better. Combination reaction is a chemical change in which 2 or more substances make one. You take a bunch of things and make a single thing. Okay? So if you were building a house, you take wood, you take nails, you take fluorine, you take all these things, put them together, and you get a house. That's what a combination reaction is. All right. So if we take magnesium metal, and magnesium, if you take a match, it will light up. In fact, if you remember pictures back in the day of like Lincoln, they had those big photographer cameras, and they would light something. That was magnesium they were lighting because it's such a bright light. Okay, so you have magnesium and oxygen. So here's our magnesium. It's a solid, closely packed atoms. Oxygen is a gas, not closely packed at all around in the air. Okay, and then you get this white powder that's left over. That's magnesium oxide. So another solid. So you've got these oxygen and magnesium particles in some sort of repeating pattern. It's a metal and a nonmetal, so it's an ionic compound. So you're going to have an ionic structure. Okay, and it's balanced. Okay, so we have 2 things making one thing, combination or synthesis reaction. Okay, most telling characteristic to recognize is a single substance product. Okay, in this case we had two elements, which is very common because that's how you make compounds. Sometimes you start with two elements, but it could also be two compounds, okay, or a compound and an element maybe. All right, here's another situation where we have a metal and a nonmetal making an ionic compound. Again, both are elements. We have a monatomic element and a diatomic element, okay, forming KCl. Notice it's balanced again. Okay, sometimes we have two nonmetals forming something. For instance, sulfur dioxide is formed from sulfur and oxygen. Okay, so if we look at it there, that's balanced, but we also have sulfur trioxide, which is a slightly different balanced equation. So what law, just as a review, what law is being observed here? This is the law of multiple proportions. You can have a 1:2 ratio of sulfur to oxygen and sulfur dioxide, but sulfur trioxide is a 1:3. Okay, so you can form different products sometimes when you synthesize things, and the conditions on which you make it and the quantities that you use may have a big role in which of the two you make, or you might make both of them in the same pot depending on the conditions. Okay, we can also have, we know transition metals can also have different oxidation numbers. So if that's the case, we could have here, we could form iron 2 sulfide or iron 3 sulfide. So you can synthesize more than one type of thing depending on conditions. Okay, the opposites of synthesis or combination reactions are decomposition. That's when you start with one thing and make more than one thing. Okay, for instance, a very common thing that was used to discover oxygen was the burning of mercury 2 oxide. It's a red substance. When it's heated, you get mercury liquid, and if you look at the concentration, the mass in your test tube, it was heavier, there was more mass compared to the mercury that's produced. So where did that mass go? It formed a gas. We now know today that that gas was oxygen. Okay? So one thing going to more than one thing. Okay? So in this case, we start out with a single compound, and we get two or more simpler compounds. So there's only one reactant. There has to be two or more products. And again, you could have elements and compounds as your products. Decomposition usually requires energy is added to get it started. So there's our three forms of energy we might use. All right, so in the car we've had a lot of talk about Takata airbags recently. And the reaction is a decomposition. Okay, in that airbag there is a chemical called sodium azide. Okay, that's NaN3. Anytime you have an azide, these are fairly unstable compounds. Okay, when it's triggered, these pellets decompose and release sodium and nitrogen. Of course, the nitrogen is a gas, and that is going to inflate the bag. The sodium, on the other hand, is reactive with water. And you're mostly water. That's why we see so many people get burnt by airbags. Okay, it's a very quick reaction. It's explosive to the point of being fairly explosive reaction we can think of. That's why it inflates so quickly. All right, so let's look at writing balanced equations for combination and decomposition reactions. Okay, so if we have combination reactions, a lot of times they're just going to give you the reactants, and you're going to have to decide what's going to happen. Okay, so combination means, okay, we're going to put two things and make one. So we know we're going to make a compound with copper and sulfide, copper and sulfur. So we're going to make copper sulfide, but we also know copper is a transition metal, so it could be one of two things. So we would have an answer if they just asked us that. One of these two things will be made, so either copper 1 sulfide or copper 2 sulfide. Decomposition of water, we have H2O, so we must make hydrogen and oxygen, so that's the only possibilities we could get. All right, so let's look at copper. I said you're going to either make copper 1 or copper 2. Okay, so if we look at copper 1, we're going to need 2 of these to balance out a sulfur. Copper 2, we're going to need 1s. Okay, so if we look at that, we're going to have 2 coppers, 1 sulfur, 1 of each. Okay, so copper 2 sulfide is that. So those are our two possible products from the combination reaction of copper with sulfur. Okay, our products for water are H2 gas and O2 gas. Okay, so if we're going to write the balance equation, we would write copper and sulfur. And in one case we're making Cu2s, in one case we're making Cus. This one is balanced, this one is not, so we would have to balance that one. Okay, water making H2 and O2, again a non-balanced. So these are all skeleton equations. This one happens to be balanced. Okay, so the copper 1 situation, we would have to put a 2 here, and now it's balanced. As I said, the second one is balanced in the skeleton form. This case, we have more oxygen on this side, so we'd have to put a 2 there. That changes our hydrogen. Okay, so we'd have to put a 2 here also. Okay, I'm going to go back just to review that. Okay, that's all we have to do. Okay, single replacement reaction. This is you go to the dance and somebody comes in and says, "Can I cut in?" Okay, that is when you give up your date to the person that wants to cut in. Okay, so that's kind of what a single replacement reaction is like. All right, so if we take potassium metal and drop it into water, you'll see what you see in the picture. You'll see a fire. Okay, and it's usually got a little purple flame. Okay, so it's a very rigorous reaction. So what are you forming? Okay, so energy is released. If energy is being released, it's probably being used to break bonds somewhere. So the potassium is a metal, you know, is going to be breaking apart from the metal, big piece of metal, but the water molecule has to be broken apart too. So if you form ions of potassium, they're probably going to react with water, so you get hydroxide, and you're also, if you're burning something, potassium itself is not flammable in a sense. Okay, the metal itself, it is and it isn't. It's actually what's burning here is hydrogen gas. Okay, so this hydrogen gas is what's burning. Okay, so OH and hydrogen gas, so that is why it's so explosive. Okay, so let's look at the reaction, because in this picture you can't see it. So we have K plus water. Okay, and you're going to get KOH, and that's going to be aqueous because it's dissolvable, plus H2. This is a liquid, this is a solid, and this is a gas. So if we're going to balance it, the K start out okay, hydrogens look okay. Oh no, they don't. They've got hydrogens in 2 places, okay? So right now we've got 3, okay? But oxygen's not, oxygen's okay right now. So we've got 3 here and only 2 there. So that means we have to put 3, because we're going to have at least 6. Now, how can we do that? This one, so we have 1 there, right? Now we have 3 oxygens, so we need 3 here. Right? Okay, so when we do that, we have 3 oxygens, so our oxygen's okay, but we have 3 hydrogens. Okay. Oh, wait a second. I think I can make this a little easier. So we have 1 there. So if we have 1 oxygen here, 1 hydrogen here, and 2, we have 3, okay. So if we really want to have 4. So if we actually just do 2 here, let's see what happens. That might be easier. So if we do that, we'll put 2 here, I think that works for us. Yeah, that's going to work for us if we do that. Okay, because if we go the other way, it's going to get too complicated. All right, sometimes it gets a little complicated. So in other words, if we have 2, then we have to put a 2 here. So if we have 2 potassiums and 2 waters, 2 oxygens, 4 hydrogens, 2 hydrogens here and 2 there, it's balanced now. That was a little tricky. Okay, now we're going to put some zinc into a solution of copper nitrate. Okay, so we're going to predict it's going to switch partners. Okay, so it's going to kick copper out and take its place. All right, so is it balanced? 1 zinc, 1 zinc, 1 copper, 1 copper, 2 nitrates, 2 nitrates. It's balanced, nothing new to do. Okay, so there's the balanced chemical equation for the first one and the second one. They're both single replacement. Okay, so one element kicks the other element out, and if both sides should have one element, but it's different on both sides of the equation. All right, zinc and copper change place in that equation. All right, we also can do this with halogens. Okay, so if we're going to have a single displacement with chlorine and bromine, okay, they're both halogens, and if we make a prediction, it should be that chlorine will kick bromine out. Okay, chlorine is more reactive than bromine. Okay, one of the ways we know that is we look at the periodic table. Okay, we know that the halogens will get more reactive as you go up the table. So if we look at our halogens, we have fluorine, chlorine, bromine, and iodine. Okay, and they are all diatomic. So as you go up, they get more active. So chlorine will replace bromine. So it must be more reactive than bromine. Okay, so you want to end up, if you look at that equation again, you have Cl2 plus NaBr. Okay, and we're probably going to make sodium chloride and Br2. So if we look at that, we start out with 2 chlorine atoms, 1 sodium, 1 bromine. We get 1 chlorine, 1 sodium, and 2 bromine. Okay, so it's not going to be balanced, but that's where we're going to start out with. Okay, so there, that is written once again. Then we just balance equations, and we see 2 chlorines here, we need 2 there. Okay, that means we have 2 sodiums here, so now we need 2 sodiums there. 2 bromines, it's balanced. Okay, actually, there is an order to something being replaced, okay? And you might want to take a screenshot of this picture of the activity series. Things that are on the top of this chart are more active because it says decreasing reactivity. Things on the top will replace things below them. So for instance, if you have magnesium with something like zinc chloride, magnesium will take the place of zinc. However, if you have zinc and magnesium chloride, zinc is below it, it's less reactive, it doesn't kick it out. Okay? It means that magnesium just says, no, you can't cut in. Okay? So iron will replace copper, but iron does not replace zinc or calcium because they're more reactive. So it decreases as you go down. Something that's more reactive will replace any metal listed below it in the activity series. So this is something that you may want to write down and put in your memory because that's how you're going to use it. All right. As we mentioned with the chlorine and chlorine is more active than bromine, so it will replace it. Bromine is above iodine in group 7, so it will replace iodine as shown in this slide. Okay, so the most reactive would be fluorine, then chlorine, bromine, iodine. Fluorine will replace all the other ones. Chlorine will replace everything except fluorine. Bromine will replace iodine, and iodine won't replace anybody. All right, got it? Got the idea? Good. Double replacement or double displacement reactions. These are kind of interesting because what you're saying is, it's like a square dance where the partners switch partners. But there's a little caveat in it. Okay, there must be something that changes. For instance, usually when we talk about double replacement reactions, we're talking about mixing two solutions. If you mix the two solutions and you don't notice anything different, just the amount of solution now is doubled or more, and basically in solution all of your ionic compounds are ions. If they stay ions, nothing's happened. So even though they're all in the beaker, they're not really forming new substances. So it's not a double replacement reaction. Something has to occur to form a new substance. In this example here, we have lead nitrate, which is a solution, and we have added some potassium iodide. Okay? And lead iodide is a yellow solid, and it's very insoluble. And that precipitates out of solution. So we have now created something that is not dissolved anymore. So if we look at these structures here, we see the potassium iodide in solution. We see the lead and the nitrate in solution. Here we see lead iodide ionic compound all in its crystal lattice, and we see potassium and nitrate still free in solution. So there's been a change. These were all free ions. These are still free ions, but these are not. They formed a new compound. So this is a precipitate, so this is a double replacement reaction because you formed a new substance. All right, so if we look at it, I could actually say in this equation, next to PBI, I would write, if I can move my pen, it's not moving, there it is. Okay, I could write a little S there. So everything else is aqueous, but this is solid, so a reaction has occurred. So sometimes you'll hear me say replacement, sometimes you'll hear displacement. So what do we need? We're either going to make a precipitate, a gas, or a molecular compound, such as water. Okay, so that's a little trickier one because if you're in aqueous solution and you're making water, you're not necessarily going to see that. But these two are definitely a sign that a reaction has occurred, and you can see that. Okay, this one you're going to find out when you balance your equation. All right, so these are the three things that one of these things must be true. Okay, and we say usually because there's always an exception. Okay, but these three things, if one of these things occur, then you will get a double replacement if you start out with two things that are partner up already. All right, so let's go through and balance a double replacement reaction. We have potassium carbonate and barium chloride. Okay, so I'll tell you barium carbonate is not soluble. Okay, so let's walk through this. Okay, so we're going to write the net skeleton equation. So potassium carbonate and K2, CO3 has a -2 charge, so there's K2CO3, barium chloride +2, -1, barium chloride. Switch partners, KCl, and barium carbonate, which is a solid, it's a precipitate. Okay, skeleton equation. Now we're ready to balance. Potassium, we have 2, we need a 2 here. That makes 2 chlorides. We have 2 chlorides in this thing. That's all set. Move on to carbonate. 1 carbonate, 1 carbonate. Move on to barium. 1 barium, 1 barium. It's done. Last reaction we want to talk about is combustion reactions. Okay? Fire, burning, okay, are combustion reactions. So what is it? It's reacting with oxygen. So one of your reactants must be oxygen, and it could be either an element or a compound. Usually you have energy produced as the form of heat or light. Okay? Always, 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 oxygen is a reactant. Okay. A lot of times, the other reactant is a hydrocarbon, meaning we have carbons and hydrogen in them. Things like methane gas or propane gas, which are cooking gases. Okay, if you have a complete combustion, you will always get carbon dioxide and water. So if you have a combustion reaction, if you see these two products, you know that it's combustion. Now, sometimes if you don't have a lot of oxygen, it won't make carbon dioxide. It might make carbon monoxide, which is not good for us to breathe. Okay, so, or you might just make carbon. Okay, so those are other possibilities for incomplete combustion. So usually we get a large amount of heat. So as I said, methane, propane, and butane are 3 sources of fuel. Methane is natural gas. Propane comes in those tanks that people have in their houses. And butane is often used in cigarette lighters. Okay, so you have 2 things, and then you're making carbon dioxide and water. So oxygen is always a reactant. These are usually your products. So the only thing that's different is this. All right. So the hardest part of combustion reactions sometimes is the balancing if you have different amounts of oxygen. All right. So gasoline in your car. All right. So if we look at this now, look at how big these coefficients are. Let's look through and see how this was balanced. All right, so we have 8 carbons. So the first thing I'm going to do is write 8 carbons, okay? And then I'm going to go to, and I have 18 hydrogens. This is the only place hydrogens are. So I put 9 there. So right now I have 8 and 9. This is how I started it. And then I have O2, okay? So if I have 8 times 2, that would be 16 oxygens here and 9 there. That gives me an odd number of 25. Okay? So what I do is this. I say, okay, if I have everything fine, so I have, right now I have 1 here, I have 8 and 9, but I have 25. How would I get 25? I would say 25 over 2. So what I did is I went through and multiplied by 2 all the ways through, and that's how I got these coefficients. So what happens is your balancing equation, if this becomes an odd number, okay, the total amount of oxygens, put that there and then multiply everything else by 2. So go through your normal way, save the oxygens to the end, all right? And it will help you do it. So I'm going to write it over one more time. So, well, I need to go back. All right? So if I rewrite this, if I just say C8, 8HT plus O2 gives you CO2. I'm not writing the gas. I'm just doing this to show you the coefficients. Okay, oxygen is in 2 places. So I'm going to have 2 places where oxygen is. Oxygen is the last thing I do. Anytime you have oxygen, hydrogen, or some other element that's showed up twice on the same side, balance that last. So we have 8. I'm going to put 8 there. 18, 9. So how many oxygens do I have now? I have 16, and I have 9 for a total of 25. Okay, that's an odd number. I need an even number because there's a 2 here. Okay, so I'm going to take this. Well, first thing I'm going to do is multiply everything by 2, except the oxygen. And then I'm going to take this number and put it there. Okay, that's how we do it if we end up with an odd number of oxygens. If it's an even number of oxygens, it's very easy because you have a 2 there. But the math is easy. Now, technically, you do have combustions. We saw the magnesium example where you can combust and burn magnesium. So in this case, our product is not carbon dioxide and water. But as long as oxygen is one of the reactants, okay, as long as oxygen is one of the reactants, we can technically say it is a combustion reaction. Sulfur will also burn. Okay?
Good morning, Upper Academy teachers. Just a reminder that I will be uploading grades at 12 o'clock. I will be uploading grades, so please make sure that you've inputted the appropriate grade, effort, and conduct per subject area. Also, your W-2s are in, so if you'd like to pick them up, please see Ms. Volado and please sign receipt. Thank you.
Okay, so we have then these 2 cases. So if you see oxygen as a reactant, technically it's a combustion reaction. It will not form a carbon dioxide and water. Now, if we look at that, we also have 2 elements making one thing. It's also a synthesis reaction. So in this case, it's combustion technically, but we would probably classify this as synthesis or combination reactions. Okay? All right, so we've got a hydrocarbon and oxygen. So I'd like you to choose the correctly, or actually I'd like you to write it out in play posit. Balance this on play posit for me. Okay, go ahead. Remember, if oxygen is odd on the right-hand side, you need to double all the coefficients. All right. So let me go over this now. See if you got it. All right, so we have C25, H53. Waxes will have very high carbon numbers, plus oxygen, yielding carbon dioxide and water. And I'm not writing the gas and the solids and all those things. All right, so we have 25 carbons and 53 hydrogens. So that means right off the top, I'm going to have to double this. So if I do that, this is going to become 50. and this will be 53. Because 2 times 53 is 106. And I have 106, okay? So that's step one. Okay, now we've got our carbons and our hydrogens all set. Now we have to look at our oxygens. So we have 100 oxygens here. All right. And we have 53 here. So we have an odd amount of oxygens. So the 100 right now is fine, but the problem is this number here has to end up being positive. So I know if we just go through and double everything, so if we change this to 106, change this to 100, change this to 4, what does that do to my oxygens now? I have 200, and I have 106. So that's a total of 306, which I can divide. All right. Yeah, they did it wrong actually. So I can divide by 2 into 153. So it should be 153. Okay. So I'm glad I did that because their answer is wrong. All right, that's what you should have gotten. All right, here's another one. This one actually has alcohol, which has oxygen in the starting material, okay, because alcohol has an oxygen in it. So it doesn't have to be just a hydrocarbon, it can be a hydrocarbon with oxygen, or an oxyhydrocarbon, okay? So we know oxygen and we know what the products are going to be. They're still CO2. So again, now we have oxygen in 2 places on both sides. So we want to make sure we do that last. So we've got 2 carbons. We need 2 carbons there. We've got 6 hydrogens. We need 3 there. So we've got, right now, we've got, okay, when we do that, we've got 4. Let me get the pen. We've got 4 oxygens. Okay, we've got 4 oxygens and 3 oxygens. That's 7. Now, in this case, since we've got oxygen in 2 places, all right, we don't want to change this one. So we've got 1 there. So we only have to have 6. So if we put a 3 there. So if you have oxygen in 2 different places, you don't have to double it right away. Okay? You have to see how you can make it work for you. Okay, so those are pretty much the basic reaction types. You should be able to predict the products of many reactions, especially combustion. You also know double replacement, single replacement, you should be able to replace them. Synthesis, etc. So it's a tool to help you predict what sort of products you'll make. Okay, so to summarize some of these, combination reaction, 2 things making 1 thing. Magnesium and oxygen. Decomposition, 1 thing making 2 things, or more than 2 things. Single replacement, at the dance, can I cut in? If it's more reactive, yes they can. If it's less reactive, sorry, you can't cut in. Double replacement. This is your square dancing situation. You got 4 partners. You're going to switch partners. Only happens if you get a new substance, though. So 2 of the partners have to come out of solution. They have to go get their coffee break. Okay, combustion, hydrocarbon plus oxygen gives you carbon dioxide and water, or a hydrocarbon with oxygen, and oxygen gives you carbon dioxide and water. Why might you want to classify a chemical reaction? It helps you predict the products that form. Here are some general ideas. Definitions. And that's it.